Assalamu alaikum students, hope you are doing good. First of all, class, mark your attendance in a chat box, okay? So class, we just start from applications of thermal expansion today. So those students who have already done, this is a revised lecture for you. The rest of class, you have to attend the lecture, right? So we are going to start applications of thermal expansion. First of all, you all know that what is thermal expansion. When we heat a solid body, if it has property of thermal expansion, it will be expand, right? So we have already discussed about solid thermal expansion in detail. Now we will discuss its application. The most common application you are using in your daily life is thermometer, right? So when when you feel hot, your body temperature is rise, you just put the thermometer in your mouth, and and when you take out the thermometer, you have noticed that the mercury level increases in thermometer. Because why the mercury increases in thermometer? Because the thermal expansion, it has a property of thermal expansion, so that's why the mercury level rises in thermometer. So this is very common application of thermal expansion in our daily life that we are using, right? So the next application is that if you have any bottle, and this bottle is the cap of that bottle is so tight that it's very difficult to open it. So what you have to do, you just put that bottle for some time in a hot water, right? So what happened, it will be loose, because the metal, it has a property to expand, right? And then you easily open the bottle, right? So this is also another application of thermal expansion. Then if you see a third example or third application of thermal expansion in daily life, see the figure 8.18 part A. So this purple, these basically are the drivers, right? So what we have to do, if we have to join the steel plate type, these are the drivers and these are the steel plates, right? So if we have to join these plate tightly, what we have to do, we just inserted these hot driver inside inside these holes. So what happened, we just fix these drivers with the help of a hammer, and when these drivers, they are cool, they will be contracted, and in this way that the plate, they will be joined together. So this is also another applications of thermal expansion that we are using in our daily life. Then if you see the wooden wheel cars, in the center of wooden wheel cars, iron rims, they are fixed. So when these iron rims are heated, what happens, these rims, they are just slip out from the wooden wheel, right? So in this way we can use them, and when we cool it, we just pour the water from this iron rim. When they are obviously when they are cool, they will be contracted and they will be tied over the wheel. So these are the four applications that are using in thermal expansion. The first one is thermometer. The other one is if the bottle cap is tightly fixed tightly, and you just immerse in a hot water, you can easily put out the cap of the bottle. Third application is that you can easily join the steel plate with the help of a thermal expansion property, and fourth one is using in iron rims, right? The second topic is that we are going to start is bimetal strip. So all of you know that the bi mean two, and metal is basically a property which are the good conductor of heat and electricity. So bimetal strips are basically we are using the two metals that conduct electricity and heat at the same time. And strips, they are made from very thin sheet. So in bimetal strip, what we are doing, we are just taking a two thin strips that are made from different metals. In your books, the example that are given accordingly for brass and iron. So what we have to do, we just take the brass strip and metal strip and just join them. And when we heat them, what happen? After heating this strip, the brass expand more than iron. Why? Because the thermal expansion of brass is more as compared to the iron. So in this way, brass will be expanded more. So these bimetal strips, they are using in our daily life in different application. If you see the bimetal thermometers, they are especially using furnaces and ovens in which we just set the temperature and we just achieve the required temperature. These thermometer, they are automatically switch off. Normally you are using this bimetal strip in your electric iron that you use to press the clothes, right? So how do you use? You just when you just on the electric iron, what happen? You will just we will just use the iron when the temperature exceeded this brass metal, it will be just expanded and the switch will be off. So the construction of electric iron is also shown in figure 8.20. If you see, there is an electric knob that is placed over here, which is used to control the switches, right? Then you have to supply the current from this side, and from this side the heat is going to the circuit. After some time, what happened, when you just supplying the heat and temperature same time, the iron is working. When the uh, when the when the iron is just sorry, when the strip is just banded like it, so the contact will be loose from that side and the iron will be its knob will be off, right? So again we have to cool this bimetal strip, and then again we have to use the electric iron. So this is a very common application of bimetal strip that we are using in our daily life. So the next topic is thermal expansion of liquids, right? So we have already discussed about the thermal expansion in liquids. So as you know that in case of solid, the molecules, they are tightly bound together, and they have vibrating motion between them, and and they just vibrate from their mean position. And when we heat them, they will their amplitude rises and they push each other, and the kinetic energy increases, and the space is obviously increases, and in this way the thermal expansion is created in case of the solids. Similarly, if you see the thermal expansion in liquids, obviously you know that the molecules, they are not so tightly bound like in solid. So they are loose, they are not free to move, but they just have more free spaces as compared to the solid. So when we heat the liquid, what happens, their amplitude will be increases. So in this way they will push each other, and the more spaces will be created, and in this way the expansion of a liquid will be take place, right? So we can say that a thermal expansion of liquid is more as compared to the thermal expansion in case of solids, because because liquids, they don't have a specific shape. They can easily adopt the shape of any container in which they will be poured. So when liquids, they are heated, liquid, when we heat the liquid, not only the liquid is going under the thermal expansion, but the liquid that is placed in any container, that obviously that container is made from any solid, so that solid is also solid containers also go under thermal expansion. So so in case when we are studying the thermal expansion of liquids, we can observe two types of expansion. One is a apparent volume expansion, and other one is a real volume expansion, right? So now we will discuss about thermal expansion of liquids in detail with the help of an activity, right? So what we have to do, we have to just take a this next class that is shown in figure 8.21, right? So what we have to do, we have to fill this long next class with the help of a colored liquid. As it is shown in figure, the red orange color of liquid is filled in this glass, and we have to place till it at point A, right? We have to place the liquid till here. So what we have to do, now we are just note that the initial value of liquid is at point A. Now, first of all, the next step is that we have to heat this flask. When we supply heat this flask, what happened? Obviously, the heat first contact with solid, and solid has also a property of thermal expansion. So, first of all, the solid will expand. When solid will expand, the size of this flask will be increases, and the size of this flask will be increases. Obviously it has more space, then the level of liquid A will be fall from A to B, right? So we can say that the level fall of A because of the thermal expansion of this flask, right? When we are continuously giving the heat to this flask, then what happened, the expansion also obviously also take place in the liquid, and the level of the liquid will be start rising, and it will be reached at point C. So this is basically the thermal expansion of the liquid take place at point C, right? So we can say that the level, first of all, initially the level is at point A, and after that the level of liquid is fall to the level to the point D, and when we continue giving heat to the flask and liquid, the level will be rise from B to C. So normally if we see this flask, we can say that the level will be increases from A to C, but actually the level is increasing from B to C, because this is the real expansion from B to C, and this is the you can say the apparent expansion from A to C. If we didn't notice that the level fall from A to B, right? So in this way we can see that how we can see the measure the real expansion of a liquid. So real expansion of liquid can be given as apparent expansion of liquid plus expansion of flask. So you can say that the real expansion is from level B to C. So we have to write over here BC, and the apparent expansion is from A to C. So for real expansion, we have to have the apparent expansion, that is AC, and the expansion of flask, that is AB. This expansion is taking place because the size of the flask is expanded, right? So the expansion of volume of a liquid taking into consideration the expansion of a container also. So in this case, we can say that the real volume expansion of a liquids also depend upon the expansion of a liquid, as well as the expansion in liquid that is placed in that solid, that is flask over here. So the real expansion of volume is represented by beta R. R is placed for the to represent the real expansion, uh, and it is defined as basically the actual change in the unit of a liquid for 1 Kelvin or 1 centigrade, that is increase in the temperature. So when we heat it, the temperature is rises 1 Kelvin or 1 centigrade. So the real rate of volume expansion beta is always greater than the apparent rate of the volume expansion. Obviously, you can see from this equation as well as from here as well as the real expansion is always greater than from the apparent expansion, right? So if we can just write in the form of volume expansion the coefficient, we can write the equation for real expansion of liquid is written in the form of beta r. This is the volume expansion for in, real expansion. Then the apparent expansion of a. So so the the so rate of volume of expansions, they are given by beta r is equals to beta a plus beta g. Beta is the real expansion of a liquid. Beta a is the apparent expansion of a liquid, and this is the coefficient of expansion of the flask. So apparent expansion of a liquid coefficient is added with expansion of a flask coefficient, and it will give us about information about the rate of volume expansion, real expansion in container. So this is a liquid expansion in this case, right? So if you see there is a side information that is given in your book. Water on cooling below 40 degrees centigrade begins to expand until reaches 0 degrees centigrade. So there is an abnormal property that is observed in this case when we cool the water at below 4 degrees centigrade. So the time period from 4 degrees centigrade to 0 degrees centigrade, the volume of the water suddenly increases, and obviously its density will also be increases, and it will be start expanding. So this is the basically an abnormal property of the water. So when the ice is reaches at 0 degrees centigrade, it will be start contracting. So volume decrease like solid. So this is the unusual expansions of water that is called anomalous expansion of the water, right? Now open page number 191 of your book. We will do the exercise. So students, open page number 191 of your book. Encircle the correct answer from the given choices. Water freezes at, obviously it will not be a 0 degree Fahrenheit. It will be a 32-degree Fahrenheit because the fixed scale is lower fixed scales of this is the right option, right? Because if you see this Celsius scale, its lower fixed point is 0 degree centigrade. For Fahrenheit it is 32 degrees centigrade, and for Kelvin it is 273 Kelvin. So here the scale is given in the right option is given in Fahrenheit scale, so the right option is 32 degree Fahrenheit. Second is normal human body temperature is, it is 37 degree centigrade. Mercury is used as thermometric material because it has uniform thermal expansion, low freezing point, small heat capacity, all the above properties. So all of the above properties is the right option, because of all these properties we are using mercury in a thermometer. So right option is option D. Then which of the following materials have large specific heat? Water is a large specific heat, that is 4200 joule per kg per Kelvin. So right option is water. Then 5 is which of the following materials has large value of thermal coefficient of linear expansion? If you see page number 184 there and see table 8.3, There the values for these materials are given for aluminum, brass, gold, steel. If you compare these four values, you can come to the result that aluminum has a large value of temperature coefficient of linear expansion, right? So the right option is option A. Then what will be the value of beta? This is beta, right? This is beta. It's a volume coefficient, volume thermal coefficient. Beta for a solid for which has a value of 2 into 10 raised to power minus 5 per Kelvin. Right, so if the value of alpha is 2 into 10 raised to power minus 5, what will be the value of beta? We know that the beta is equals to 3 times alpha. So what you have to do, you just multiply 3 with this value of alpha, right? So if you multiply 3 by multiply by 2 into 10 raised to power minus 5, you will get the answer 6 into 10 raised to power minus 5 Kelvin. So this is the right option. Now see part 7. Large water reservoirs keep the temperature of a nearby land moderate due to A option is low temperature of water, B is low specific heat of water, C is less absorption of heat, and D is large specific heat of water. So the right option is option D, right? Then which of the following affects the evaporation? Option A is temperature, B is surface area of the liquid, and C is the wind, and D is all of the above. Obviously, we have discussed during the lecture that evaporations also depend upon the temperature, surface area of a liquid, and wind. So the right option is option D, that is all of the above. So students, you have done all the question in your notebook. Those students they didn't complete their notebook work, you have to complete their all the question answers regarding unit 8, right? So question 8.2 to 8.5 we have done in the class. 8.6 is also done, but these are the for those students those who didn't done yet, right? So see question 8.6. What is thermometer? Why a mercury is preferred as a thermometric property? You just give the definition of thermometer, and you know that mercury is a thermometric material, so you have to write all the properties of mercuries, right? Then the next question is 8.7. Explain the volumetric thermal expansion. You just have to explain about the volume thermal expansion. Also, you have to do the calculations that are discussed in the class till beta is equals to 3 alpha. Okay boys, if you haven't done these questions, you have to write all these questions in your notebook. So these are the question answers, so just you have to these topics are already discussed in the lecture. You just have to write the answer in your notebook, right? So this is the 8.7. Then if you see question number 8.8, define specific heat. How would you find the specific heat of a solid? First of all, you have to give the definition of specific heat. Specific heat of a substance is the amount of heat required to raise the temperature of 1 kg mass of that substance to 1 Kelvin. Then you have to write these formulas as well. C is equal to delta Q by M delta T is is the relation for specific heat of a substance, and the unit of specific heat is joule per kg per Kelvin. The next question is 8.9. Define and explain latent heat of fusion. You give the definition of latent heat of fusion, its relationship, and write its unit. Then the last question is 8.10. Define latent heat of vaporization. Latent heat of vaporization, you have to give the definition of it, then write its relation, and then give its unit. Yes, 9B we have okay. So the last question is 8.14. Open your book, page number 192. What is meant by evaporation? On what factors evaporation of a liquid depends? Explain how cooling is produced by evaporation. The answer of this question is on page number. Uh, you open page number 182. The definition is written in pink box. You have to first write the definition, that is evaporation is changing of a liquid into vapors gaseous state from the surface of a liquid without heating it. Then come to page number 183, and these are the four factors that are given over here: temperature, surface area, weight, nature of the liquid. You have to write all these factors. And the third part of a question is that explain how cooling is produced by evaporation. So for answer of this question, you have to come on page number 182, last paragraph, third line. During evaporation, fast-moving molecules escape out from the surface of the liquid. Molecules that have lower kinetic energies are left behind. This lowered the average kinetic energy of the liquid molecules and the temperature of the liquid. Since temperature of a substance depends on the average kinetic energy of its molecules, so you have to write answer till here. Now, if you have any question regarding this lecture, you can ask me. So class, if you have any confusion, you can ask me. Otherwise, I have to end the meeting.